Next problem up, I want to look at number 18, 1 over x from x equal 1. At 1 we are at 1, 2, 3 we are at 1/3, so you're only talking about this piece of the graph. And here we could easily see there is no local extreme value, no local extrema, and there are none, no absolute max or min. Alright? The graph of a sine wave, the graph of a sine runs up 1 unit, so that's 0. And this is only running from 0. Oh, that's it, pi over 2. Actually, let me just enlarge that a bit. Let's say pi over 2 is right there. Right? Now, this is not included and this is included. Well, obviously it's increasing all the time, so we have no local extreme values or extrema. But we have an absolute max of 1 at x equal pi over 2. Hopefully we're following along. If I want to sketch a graph of a cosine, I start on the amplitude, run down pi over 2, pi, 3 pi over 2. That's included. Negative pi over 2, negative pi, and negative 3 pi over 2. And here I'll say I have a local maximum of 1 at x equals 0. I have local minimum of negative 1 at x equals, so this was pi over 2, this was pi, and this is 3 pi over 2, negative pi over 2, negative pi, and negative 3 pi over 2. So at x equal, wouldn't that be negative pi over 2, negative pi and pi? Negative pi and pi, and this is the highest point. That turns out to be the absolute maximum, and these are the lowest points. That turns out to be the absolute minimum as well, both of them. Alright, now you could separate those if you wish. You could say, oh well, we have an absolute max at x equals 0, that's fine, and we have an absolute min at x equal negative pi or pi. It makes no difference. I think the book separates between those, not a problem. Now, Fermat's theorem. Somebody was able to get their name on a theorem. It says if f has a local maximum or local minimum, and this exists, then the derivative equals 0. Now let me show you something we haven't talked about yet. And this definition falls from that theorem. Critical numbers, we use Cn for critical numbers, of a function f is a number in the domain such that f prime of c equals 0 or f prime of c does not exist. Well, that's what they're going to amend Fermat's theorem. Let me show you something really quick. If I was to go back and look at this, a couple of things we should be considering. Actually, let me mimic that graph. I'll mimic it right here. Do you notice if I was looking at these graphs left to right, do you notice the slope of the tangent is 0 at every point where there is a maximum or a minimum local? Not only that, do you notice if the function is decreasing, the slope of the tangent is negative, and if the function is increasing, isn't the slope of the tangent positive? So if I draw a tangent line right there, isn't the slope of that line negative? And notice the function is decreasing, and those go hand in hand. I'll point that out as we move into the sections. For now, they want us to find the critical numbers. And why do you find the critical numbers? Because we want to check for maximum and minimum. How do you find critical numbers? You take a derivative. 3x squared plus 12x minus 15, and you set it equal to 0 or check where is it undefined. If there is a maximum or a minimum, it must happen at a critical number. So if I factor a 3 out, that's x squared plus 4x minus 5 equal to 0. And now easy factoring. So those are critical numbers. They could be a maximum or a minimum, or they could be neither. They could be nothing. But that's one possibility. And where's the derivative not exist? Polynomials exist everywhere. And how about this problem? Well, on this problem, if I take a derivative, this is actually 1 over, this is 4 minus x squared to the 1/3. You bring the power down, subtract 1 from the power, times the derivative of the inside. So g prime is actually negative 2x over 3, the cube root of 4 minus x squared squared. If I was to say, where does g prime equal 0? That's easy. A fraction equals 0 when the top equals 0. And if I was to say, where does g prime not exist? Well, that's very easy. 4 minus x squared equals 0. That's when the denominator equals 0, right? Now, there is a restriction on the domain of this. Actually, there isn't. I'm sorry, take that back. That's a cube root. So, only not equal to 0. That's when 2 minus x into 2 plus x equal to 0. So, x equal 2 or negative 2. The critical numbers, which could be possible maximums or minimums, happen wherever the derivative equals 0 or the derivative does not exist. Cool? Let's look at another problem, everybody's favorite. If I take a derivative of that, that is 4 minus derivative of tangent is secant squared of theta. I want to know where that equals 0. If you took our math 8, this is section 2.3, secant of theta squared equal 4, secant of theta equal plus or minus 2, or simply cosine of theta equal plus or minus 1/2. That happens when theta equal what? Well, the solutions here are infinite. So reference angle would be cosine equal 1/2 at pi over 3. Where is cosine positive? Well, it's positive in 2 quadrants, and it's negative in 2 quadrants. So it's in all quadrants. And wouldn't you say that would be pi over 3 or 2 pi over 3 or 4 pi over 3 or 5 pi over 3? And wouldn't you add 2 pi k to each of those? And that's all you need to do. So for now, when they ask us to do this in the next few sections, they'll give you a limit on the domain, but it's just for practice. So if I look at closed interval method, to find an absolute maximum and minimum on a closed interval, find the values of the critical numbers, check the endpoints. The highest of those is the absolute maximum, and the lowest of them is the absolute minimum, without actually figuring out any local. Talking about absolute. So I'm already gonna take f of 0. F of 0 is a 5. I am gonna take f of 4. F of 4 happens to be a 5 plus 54 times 4. What is that? 16, 21 to 16. And minus 2 times 4 cubed 64. That's negative 128. and that turns out to be 93. So I have two values. For now, it seems this is the absolute maximum, this is the absolute minimum, but I know nothing about this graph except if I take a derivative, I'll figure out a bit more. If I take a derivative, that's 54 minus 8x squared equaling to 0, right? That would be, that's 6x. You guys say something. And that is, if I take 6 into 9 minus x squared equals 0, that would mean x equal negative 3 or positive 3. Those are the critical numbers, but negative 3 is not in there. 3 is the only other candidate. If I take f of 3, that's 5 plus 3 times 15, 162, minus 3 squared, 27 times 2, 54, if I'm not mistaken, right? And what would that be? That would be 167 minus 54, 3, 113. So wouldn't you say this would be the absolute maximum and this would be the absolute minimum? One more to go, and here, if I have time, I'll graph it. F prime is actually 3 into t squared minus 4 squared times 2t. So where does that equal 0? That's when 6t into t minus 2 squared t plus 2 squared equals 0. T equal 0, 2, and negative 2. All of these points are valid. If I take f of 0, well, that's easy. Put a 0 there. That's negative 64. F of 2, that's a 0. F of negative 2, that's a 0. Those are the local. How about those? How about f of 3? If I put a 3 in there, that's 9 minus 4, that's 5, that's 125. Wouldn't this be the absolute maximum? And wouldn't this be the absolute minimum? And if I looked at a rough sketch of this, I know how to graph this from college algebra. So this has, at 0 you are at negative 64. Let's say that's negative 64. I have at 2 and at negative 2. Isn't the multiplicity 3 on each? Doesn't that mean that, and this behaves like x to the t to the 6? Shouldn't that behave like a cubic right there? And shouldn't that behave like a cubic right there? And if I go ahead and look at this graph and just worry about it from negative 2 only, to 3, of course the graph is out of sync. Do you see that this is the highest possible point and this is the lowest possible point? Pretty cool, huh? When you put everything together, that's what calculus does. And there's your homework. It's a lengthy homework. 1 through 57 odd is an extremely important section. It's going to set the basis for all of chapter 3, which is the busiest work of 5A. And skip number 43, that's a hard problem. We skip hard problems. Alright.